Hey guys, welcome to another episode of Tech Topics. My name's Chris and we're going to be talking today about erasure coding. Now, erasure coding is a feature we introduced in NOS version 4.1.3 as a tech preview. This means we don't recommend it for production workloads, but still it's going to rapidly become a core part of our platform. So what is erasure coding? In our system, you probably are already familiar with our replication factor, where we keep 2 copies of all the data. Erasure coding takes those replicas and reduces them down to a number of parity blocks. This allows you to save a ton of space on the replicas and increase the usable space in the cluster. So let's take a look and see what that looks like. Here we have a 4-node cluster, or 1 block. Now, in a normal system without erasure coding, when we write a piece of data, say data A, we will immediately replicate that somewhere else in the cluster so that we have a backup copy. Same for B. With erasure coding, we have what's called the erasure code, and this is a ratio. This ratio says how many blocks to reduce to how many parities. So, in a 4-node cluster, we would use a 2-to-1 code. This is because with the code, we need the summation of this plus 1 in order to have rebuild capacity. So, with a 2-to-1 code, we will take these 2 blocks and reduce them down to a single parity block. This gives you space savings. Now, how much space savings? Let's take a look. Say that these 2 blocks are each 4 gigs of data. We're storing 8 gigs of real data with the 2 replications in 16 gigs of actual space. With the erasure code, now we're storing 8 gigs of data in only 12 gigs of actual space. So you have an extra 4 gigs to work with here. And this continues scaling up. So for example, if we were trying to store 8 terabytes of data, we would actually only need 12 terabytes of space. Now you might notice that we didn't touch this block at all. This is because if one of these nodes fails, the parity block needs to be on a different node than either of the pieces of actual data. So we need to have a spare block in case this node fails. We can put the parity block over here to rebuild the cluster and bring it back whole. We can't change the erasure code on the fly without recoding all of the data, which is computationally expensive. Now, the system makes this very easy to enable and use. You actually just turn it on the container, and we will choose the best erasure code. So if you have a 4-node cluster here, let's bring this node back online now, we will automatically turn on erasure coding at a 2-to-1 ratio. Say later on you add another block. The system will automatically code the new data in a 4-to-1 ratio. This is the maximum that it will go on its own, as after this the space savings gets proportionally less and less, making the extra computational power required to calculate the code not worth it. So by default, the system will choose for you a 2-to-1 to a 4-to-1 code in an RF2 cluster. So as I mentioned, this can be computationally expensive because now if, say, data A here gets rewritten and becomes C, we now have to recalculate this parity block as A prime is no longer what it was based off of. And so we've got to go through, calculate it again. Because of that, erasure coding isn't recommended for all workloads. In particular, workloads that have a large amount of overwrites are not recommended for it. Curator is the guy who's in charge of doing the erasure codes, and he only runs this on cold data. By default, it does it on data that hasn't been written to in an hour. However, you can configure that from NCLI to increase the delay. So for example, only run it on data that hasn't been written to in a day or a week or a month, depending on your system and your current needs. One other thing to note is that the erasure coding does not work on a 3-node cluster by default because there won't be the rebuild block. With only a 3-node cluster, we have nowhere to put the parity block if one of these nodes fails, therefore we won't allow erasure coding to run. Some other limitations of erasure coding right now is that it doesn't work with block awareness. When it does eventually work with block awareness, you will need a number of blocks equal to your code plus 1, rather than the number of nodes. You might notice some similarities here to RAID. It's kind of like RAID across a cluster, so on a per node basis rather than a per disk or a per host basis. So it gives you the resiliency and the data protection that you've come to expect from Nutanix, but with some additional space saving that we get from reducing our replicas down to a single parity block. And one other final thing to note is that the only time that you're going to see this parity change is that if you had an RF3 cluster. In an RF3 cluster, you'd be using a K of 2. So a 2-to-2 ratio doesn't make any sense because then you're storing the same amount of data in the same amount of data. So with a RF3 cluster, you'd see a 3-to-2 or a 4-to-2 ratio. And once again, the system will automatically calculate this once you turn it on. That's all there is to erasure coding. So you can tell it's not exactly a really complex technology, and we hide a lot of complexity from you, the user, as the goal is. We want it to be simple. You turn on, you get more space. The system automatically figures out the best way to do it for you. I hope this has been really informative, and I hope you check out this new feature that's really exciting, and we're really happy with how this has turned out. Thank you for tuning into another episode of Tech Topics. Have a great day.